Hello, my name is Ryan. Welcome back to another RC video. Now in this video, we're going to be talking about cogging that occurs within our brushless motors. Now cogging may not be exactly what you thought it was, so let's find out. So the first thing that we have to answer is exactly what cogging is and how it works and why it works the way it does. So we have to go back maybe 5+ videos ago when we were talking about slotted motors versus slotless motors. Now if you remember, a slotted motor has iron laminations that represent the core within the stator. Now those laminations are stacked up on one another, and as they stack up they produce a thickness that essentially represents the length of the brushless motor. Now if you were to take the cross section of that lamination and look at that, you'd have what are known as the slots that make up the holes where you actually place the wires. So the copper wire that would go in a brushless motor to serve as the windings would go down one of the slots, around the back or front of the motor, and come down another slot over here. And it would be wrapped around what is known as an iron core. Now the reason why this iron core is important is because it has an interaction that plays upon the rotor. Now the rotor on brushless motors are made up of permanent magnets. They can be 2, 4, 6, 8, 10, 12, a whole bunch of different pole counts, and that represents how many north and south poles that we have in a brushless motor. And the reason why this is critical and important is because the interaction between the rotor and the stator is exactly what makes up cogging. Cogging occurs in a slotted motor. It does not occur in a slotless motor. So what happens in this slotted motor is that you have that iron core and you have, let's say, a 2-pole motor. When that north pole ends up reaching that core and it hits around this area, there's an interaction. We know that iron and steel, it's a ferrous material that interacts with the magnet, and as you get that interaction you are able to feel it. It's that magnetic pull. So I have 2 examples here in front of me. Let's grab one of them. So this is a brushless outrunner, and this brushless outrunner is fairly large. I can't remember the exact pull count within this motor. However, what I'm able to do, I can feel the cogging that occurs within this motor. All I need to do is take the rotor of the motor, so that is the can in the case of an outrunner, and I can rotate that. So as I apply a force, I can feel all these little notches. So I'm trying to apply a continuous force on this brushless motor, but it doesn't allow me to do that. It's jumping around because I'm feeling all the bumps. Now, of course, if I spin it at a much greater speed, then I can go through that. And it looks like I'm continuously moving that motor in a very smooth fashion. But even though it looks like that, I'm not able to rotate this motor in a very smooth fashion. So at slow speeds, extreme slow speeds, it's jumping around quite a bit. Now I have another example in front of me. This happens to be an in-runner motor. It came out of a brushless boat made many years ago, probably in 2007 or so. It's known as the Super V, and the reason why this is important is because this motor specifically in this boat contains a 6-pole rotor. Now 6-pole rotors in terms of cogging is probably the most intense amount of cogging that I've ever felt within a brushless motor. And when I refer to the intensity of cogging, I'm referring to the cogging torque that needs to be applied to overcome the cogging phenomenon that is occurring here. So if I try and rotate this brushless motor, I can't actually rotate it. It's so strong, the magnetic force that's being created here between the magnet and that iron core in the brushless motor is so strong I can't rotate this motor at all. I would have to put some sort of collet on here in order to give myself a little bit more leverage, and then I can rotate it. And even when I do that, it's very strong. There you can very much see how cogging torque actually makes a very big difference. I can't even rotate this shaft with my hand. It's that strong. And this motor still runs, so it's not, one might say, well, it's because this motor is all seized up. No, this is a perfectly running motor. It is not seized. I can rotate this motor if I had a little bit more leverage. So both of these motors are sensorless motors. So let's talk about the next question that we have. Can we have cogging occurring within a censored motor? So a censored motor It's very much like a sensorless motor. You still have iron cores that represent the stator in a slotted motor. You're still going to have your magnetic rotor, whether it's even an outrunner or in-runner. Most censored motors are going to be in-runners because they're more common on brushless RC cars and trucks where you need that higher RPM. So the only real difference between a censored motor and a sensorless motor is the fact that your censored motor has the sensors that allow your brushless speed control to know the exact position of the rotor. So does cogging affect a censored motor? Well, of course it does, because we defined cogging as the interaction between the magnet, so our rotor, and that iron core. A censored motor still has that happen, so cogging still exists in those motors as well. And you'd be able to feel it by, again, taking that, censored motor and trying to rotate the shaft. So let's go to our third question. How does cogging torque affect the performance of our RC vehicles? Well, I do believe that this is exactly where confusion of cogging actually started from, or kind of is generated from. So the only real area where the cogging torque can affect the performance is in the startup. Now note that the startup of the brushless motor on a sensorless motor is going to be relying on the speed control to figure out its relative position. The synchronization between the motor and the speed control is not what cogging is all about. That seems to be kind of the confusion of this whole term. That has to do with the synchronization of the two units, the motor and the speed control. Cogging can actually come into play where the brushless speed control sends a pulse down to the motor. It doesn't know where this rotor actually exists. It sends a pulse to the windings, and then the rotor rotates by, let's say, a quarter turn. So it goes and rotates a quarter turn. However, it lands right at a spot where the cogging torque, brings it back an eighth of a turn or a 16th of a turn, a very small amount. And then it kind of loses its position for a second until it sends another pulse and moves it again. So you do have the cogging torque kind of interacting even with that synchronization process. And speed controls these days do a very good job as to determining the location and figuring it all out and dealing with this sort of cogging torque. I do know that this motor here, depending on how I actually set it up, and if I run it at a lower voltage, I could definitely tell that the synchronization process was a little bit more challenging, and I would say that cogging did also make that worse. If I changed this motor out, used the exact same speed control, and used it on a 2 or 4 pole motor at that same voltage, it would have an easier time actually getting in sync. So once the motor is turning, then all of the cogging torque it doesn't even really come into play. So the last item that we have is, can you actually feel the cogging torque in your RC application? And the answer is yes. Very similarly to how you can hold that motor in your hand and you can kind of run through the rotations right there by feeling the interaction between your rotor and the core of the motor, those laminations. You could do the same thing in your brushless RC car. Now it's best if your car has very high gearing by just pushing your RC vehicle very slowly across the ground. As you're pushing the RC vehicle, you may actually hear some sort of noise that is generated. As you're pushing it, you're going to have the same sort of phenomenon happen as you're building the torque of the cogging torque. As you're building it on the positive side where you have to put force into it, and then you'll feel on the negative side as that cogging torque is actually, providing torque to you. So you'll be able to see the backlash of the gears. You may actually hear them. It might actually be quite loud during this sort of period. In general, this is the only spot where you're able to hear the cogging torque actually taking place. So what I have here is a 1/8 scale on-road RC car. Now it has very, very high gearing. It's geared for well over 100 miles an hour. So I'm going to go ahead and push this radio control vehicle, and hopefully you'll be able to hear exactly what I mean by the cogging torque that is applied. So as I'm pushing it, I'm going to be forcing the motor to try and turn, as I'm going to be pushing through that cogging torque. And then once I reach the peak, then it's going to, the opposite's going to happen, where the motor magnet is going to push the rotor away, in which case the gear is going to start to cause that noise of backlash. So let's hear it as I push it. So it's very obvious what's actually happening here. That's exactly what Cogging Torque is. So there you go. Now I am going to be talking about in the future a video that has to do with censored motors and sensorless motors. We're going to be going about the advantages of them, the disadvantage of them, how they work, where they work in the range at low RPM versus high RPM. We're going to be covering all of that. So stay tuned for that. Make sure you subscribe so as soon as these videos come out, you're able to watch them right away. I hope you like this video and I'll see you in the next one. Thank you for watching.